Good afternoon, everybody, and thank you for joining us. My name is Dale Norton. I'm the sales director of Meyer Supply. Similar to many of the individuals tuned in this webinar today, I've been in this industry for a while, and what I enjoy most about it is that every day is different, and there's always new challenges. So today we know that we have some common refrigerants that are being phased out. Now we are tasked as a group to provide solutions to the industry. About a month ago, Meyer Supply hosted a webinar, Meyer Supply and Chemours, hosted a webinar that reviewed the impact and regulations of the AIM Act. The AIM Act now is changing some of what we do today. So many of the refrigerants that we use on a regular basis are going away. We know this. We have some time, but currently availability is questioned, and I'm sure some of you are already seeing pricing. So educating yourself on the associated technology becomes critical. You're either prepared to make the change or you're going to be forced to do so later. There's also some logic to being able to confidently sell your customer a long-term solution, and that's perhaps something that maybe your competitor isn't doing. And for service purposes, it also makes sense to provide a consistent solution and provide a refrigerant choice, liken it to having to carry 12 refrigerants on your truck rather than carrying maybe 2 or 3. So today we want to specifically talk about some legacy refrigerants and changeouts to an HFO refrigerant, 449A or XP40. We want to understand the process and what to expect, and these things are going to make a difference for you. It becomes important because as you come across the need to make some changeouts, a lot of considerations that we think about as technicians anyways, oil control, system capacity, head pressures, component sizing, and the compatibility of some of the components, and even long-term system reliability, not to mention making sure that we're in compliance with regulations. So our presenter today, those are some things we'll be addressing today, and our presenter today is Andrew Padua. Andrew is a technical service engineer for Chemours Refrigerants. He holds a master's degree in chemical engineering from Lehigh University. Over the past 9 years with Chemours, he has primarily been focused on the development of next generation refrigerants for the HVACR industry, including training the industry and how to complete retrofits to lower GWP alternatives from HFCs and HCFC refrigerants. So also with us today, accompanying us was Mark Love from Chemours. He is regional sales manager for Chemours, and he also is a refrigerant consultant for Meyer Supply. We rely on him heavily on him. So Kate Becker from Chemours, also behind the curtain, helping us with the presentation. I'm sure you'll have some questions as we progress through the presentation. Be sure to use the questions section of the GoToWebinar tool, and you can submit those questions. We'll address either as we go through or save for the end when we have time. If there's anything that we don't get time to answer during the presentation, we'll respond directly to you with the email. And also remember, even after this presentation, that Meyer Supply, your local branch, you've got questions, we can either answer them from the resources we have at the branch, or we also can rely on Chemours and contact them as needed. So with that, I'm going to hand it over to Andrew. It's all yours, Andrew.
Awesome. Thank you, Dale, and good morning, everybody. Like Dale mentioned, my name is Andrew Pansula, so I'm one of the tech service engineers at Chemours. Today, we're going to cover retrofitting legacy HFC and HCFC refrigerants to lower GWP alternatives. So as Dale mentioned, if you have any questions as we go through this, please use the chat box. I'd like to think I'll take the easy ones and maybe give the harder ones to my colleague, Mark. So with that, Dale mentioned before that the first webinar was really around the regulatory update and what's going on from a regulation perspective in the HVACR industry. So we're not going to really focus on that too much today, but I think the one thing we wanted to focus on was really what is going on, and I wanted to reinforce what's going on in the industry with the AIM Act. So that's the one word you may hear more often than not, and really what that is that's the phase down of HFC refrigerants in the industry. It's not like what happened with 22, where they're specifically saying on a certain date you can't use R22 anymore. But rather it's more looking at taking a total HFC quota, so pretty much your GWP multiplied by the pounds of your refrigerant, and phasing that down over time. So pretty much what this means for you guys and really for the industry as a whole is business as usual is really going to change. And a lot of the industry, to meet this regulation, really is going to need to start to look at lower GWP alternatives from both a new install perspective, as well in some cases of being proactive in retrofits. So a lot of the presentation we're going to cover today is around HFC, so 404A retrofits, because that's really the new one, but we're going to cover everything in this retrofit from 22 retrofits to HP80, 408A. I mean, there's a lot of different equipment out there that people are looking to retrofit. So we want to do a pretty high level overview in this hour around really what we're seeing from the field and recommended steps for how to properly do these retrofits. So with that, if you look at the history of refrigerants, I mean, it's been an industry that's transitioned a lot. From the 1930s, the CFCs, some of the better performing refrigerants, but they had high ozone depletion potential and very high GWPs, to some of the more non-chlorinated blends like the HFCs, to now really it's a mix of the industrial chemicals, things like CO2, hydrocarbons, and then the HFOs and HFO blends, which is what we're going to talk about primarily today. A lot of those HFO blends really are the only way you're going to be able to work with the existing system designs while maintaining the capacity, safety, efficiency of the system. Really, one of the interesting things that we always get asked is there ever going to be a silver bullet, if you will, for the refrigeration world? Like, is there ever going to be one refrigerant that's just going to work in everything, like the 12 days or the 22 days? And I mean, unfortunately, I think those days are to a certain degree behind us. We'll talk about some of the retrofits are certainly consolidating refrigerants. So you're going from, 4 refrigerants to 1, but really the refrigerants of the future, it's really a balance based on whatever your goals are, and it needs to balance performance, safety, sustainability, and total cost of ownership. And really the balance between those 4 key metrics is going to be how a refrigerant retrofit is going to make sense, or what refrigerant you should use in your new system. So the base HFO molecule really is 1234YF. So if you're familiar with auto air conditioning, 1234YF is actually already being used in that segment of the industry. So 1234YF is very similar to 134A from a capacity and an efficiency perspective, but it is what's considered to be mildly flammable. And as we go through the webinar series with Meyer Supply, I'm sure down the road we'll have a mildly flammable webinar. That's not really going to be the focus of today, but pretty much what you need to take away from it right now is it has what's considered to be an A2L classification. So you're not going to see like neat 1234YF as a retrofit option, but it provides a way as a blend component to be a very valuable refrigerant in the toolbox. So for an example, you take a refrigerant like 407A. 407A has 3 components. It has R32, R125, and R134A. And one of the products we're going to talk about today at 449A, that's a 4-component blend with the 3 components that I just mentioned in addition to 1234YF. So what 1234YF allows you to do is take some of the 134A out of the 407 blends with a GWP of roughly 1300 and then replace it with a molecule that has a GWP based on the AR5 standard of less than 1. So it's a way to really kind of continue to maintain or exceed that performance that the industry is used to while getting lower GWPs. And you may think, well, aren't you adding a flammable component? Does that do anything to the system? And the answer is, or the blend flammability, and the answer is no. I mean, if you take something like 410A, for example, 410A is actually 50% R32, which is also a mildly flammable refrigerant. So the industry, for as long as it's been here, has been blending mildly flammable components with non-flammable gases to make non-flammable blends, which is what we'll cover with some of the retrofit gases later in the presentation. So this is a good slide to screenshot, I'd say. There's a couple of them, and I'll make sure to point them out as we go through this, but this is definitely a good one. This is essentially the high-level roadmap of what products are available and in what segments. So if you have 22 equipment, for example, the green boxes are the non-flammable replacements in the Chemours portfolio. So 449A is our refrigerant of choice as a lower GWP 22 alternative. For 404A, you'll also see that 449A is listed for that, and we'll cover the retrofit slides for those gases on some of the later slides. And then for 404A specifically, there's another product on there. It's not really going to be the focus of the presentation today, but I do want to make sure you're aware about it, of 452A. So 452A has a GWP of 1945, and it's used more in specific applications, things like transport refrigeration or low temperature condensing units. So things that really have issues with demand cooling. My only guidance with that product specifically is if you're ever interested in using it, please make sure that the application you're looking to use it in has SNAP listing. Very generally, when looking at what makes sense for your system, especially if you have 404A, 507, 22, the lower the GWP you can go, the more, I guess, leeway you'll have in refrigerant selection. So essentially 449A, going back to what we were just talking about with the different blend components, 449A really is the lowest GWP you're going to get while maintaining or exceeding the 22 404A performance, and also still being a non-flammable refrigerant. If you want to go lower in GWP, then really you start talking about a trade-off, and the trade-off could be capacity, it could be glide, it could be flammability, and all those things wouldn't really make it a good retrofit gas. And for that reason specifically, one of the questions we get a lot is around, hey, if I retrofit everything to 449A, is 449A going to be around long term? And I would say definitely. I mean, it's really one of the only products that can be used in those existing 22 404A 507 systems with such a significant drop in GWP. In the 134A world, you have 513A. So 513A, actually, it's been around as long as 449A. I would think most people on the call by this time have probably heard of 448A, 449A, all those products. You may not have heard of 513A. And one of the reasons for that is 513A has been, it's certainly had a little bit of a cost delta compared to 134A. However, with the AIM Act and lower GWP refrigerants being more incentivized, 513A certainly is a product that will be of more note and interest moving forward. I mean, it's almost, I think it's a 55% reduction in GWP versus 134A, while also maintaining that 134A-like performance. So in the medium pressure world, I mean, that product makes a lot of sense. There are black boxes here, which we're not going to cover today, but essentially those are our lower GWP or lowest GWP XL series refrigerants, which are A2L refrigerants. So they do have a different safety classification than the 449s, the 452s, and the 513As of the world. So those products are going to be looked at in new systems. You can find case histories in Europe today where they're evaluating these refrigerants. I'd say in the US, the codes and standards are still being updated and really trying to be finalized to safely use these products in the industry. But I wanted to throw them out here just so you know that these are being developed and evaluated, and I would expect in the future you might start hearing more about these refrigerants. The last box here that I want to cover for 410A, Notice there's no green box for 410A. So currently, there is no retrofit gas for that equipment. 410A will continue to have to be serviced with 410A, and there's reasons for that that are beyond the time that we have in this webinar to go through. But very generally, 410A equipment will continue to be serviced with 410A, and then we have 454B, which you might have heard of, which is actually being launched by some of the major AC OEMs such as Carrier as a lower GWP alternative to 410A for new equipment only. And I cannot stress that enough. You're really only going to see 454B in that new equipment. It's not a retrofit gas for the existing 410A equipment, but it does provide a way for new equipment to get to significantly lower GWPs than 410A. So this is the high-level refrigerant roadmap, and now we're going to get into the more interesting part of the presentation about the retrofit considerations. So this is really the world I think we're all going to be living in. And when looking at a retrofit, at least from my perspective on the engineering side, my first and foremost goal is always to keep that existing equipment running. It's not really going to be a great retrofit gas if you're changing all the heat exchangers, the compressors, and in short, making an entirely new system. So having a gas that keeps that existing equipment running while also being simple and easy to service, that provides minimal cost and long-term compliance is all really important when trying to figure out what refrigerant you want to retrofit to. On the refrigerant side of things, making sure that the refrigerant is safe. So the easiest way to think about that is if you're working with a HCFC refrigerant, that is going to be a A1 non-flammable, low toxicity refrigerant, and anything that you retrofit in it also needs that A1 rating. So the refrigerants we talked about here in the green boxes, they all have that A1 rating, and they have the same safety as the HFCs or the HCFCs that you would be retrofitting to. Acceptable performance match. Being on the engineering side, performance, I'd say, is one of the more general terms that I always get an interest out of hearing what that actually means. So from a refrigerant point of view, when I think of performance, I'm thinking of capacity, efficiency, mass flow rate, suction pressure, discharge temperature, and temperature glide. And then based on those metrics, what recommendations or changes do you need to make to your existing system such that you're getting the optimal performance and cooling out of your equipment? So I'm going to cover the 22 conversions very quickly. 22 conversions have likely been going on for a while, just based on 22 being phased out of the industry in 2020. But as a hopeful reinforcement to what's going on, these are the 8 steps that we recommend for any R22 retrofit. So step 1 is reviewing the retrofit guidelines. So essentially, we always equate that to reading the directions before use. So the retrofit guidelines, it's a very dynamic document. So it's something that we are always updating based on what we learn from the field and really what we learn about what works well. It also includes your PT charts and all the checklists that you need to successfully do the retrofit. Obtaining baseline data while running on R22, that's a very generic way to say a retrofit is not going to fix an existing problem in the system. So if you're having a problem, you want to obtain that baseline data with 22 to make sure, do my pressures make sense of where they're at? Is my low side pressure where I expect it to be? Am I getting the superheat subcooling on 22 that I really think I'm supposed to get? Because if you're getting weird or data that's unexpected on 22 when doing a retrofit, that same result could be expected post retrofit. With R22 conversions, the big thing is changing the oil to POE. So 22 systems are going to be running on a mineral or alkyl benzene oil. We generally recommend two oil changes for each retrofit at a minimum. So POE is a pretty good solvent, and that first oil change, especially if you have a 22 system that's been running for a long time, the POE can clean the inside of the lines and start circulating a lot of things that you likely would not want circulating in your system. So the first oil change will, one, help get any of the mineral oil out of the system, in addition to getting any of the dirt and debris that may come from the POE. The second oil change will make sure that you get your residual mineral oil percentage down even lower. In our retrofit guidelines, I believe we try to get down to roughly about 10% or less residual mineral oil before going to a new HFC, HFO refrigerant. Recovering the R22 is a key one. Make sure you recover all that 22. And then the other big one with 22 retrofits is changing the critical elastomeric seals. So R22 and chlorinated refrigerants, they're chemicals. And because they're chemicals, they have certain other chemicals or materials that they have an affinity for. And one of the ones that they certainly have been known to interact with is elastomeric gaskets. So while a system is running on a chlorinated refrigerant, the chlorinated refrigerant dissolves into the gasket and causes the gasket to swell, which is great when the system is running on a chlorinated refrigerant. However, when you do the retrofit to a, whether it be 449A or even in the past 407A, those retrofits, the way those seals swell is different for HFCs and HFO based refrigerants. So the system, if you do not change those critical elastomeric seals, can be more prone to leaking. So it's generally good practice to make sure that you're always changing those critical elastomeric seals when doing a retrofit from 22 to another gas. The other steps are pretty straightforward: evacuating the system and leak checking, charging the system with 449A, starting up and monitoring. I mean, generally your charges are going to be pretty similar, probably plus or minus 5% depending on design. And then leak check, label system, and optimize set points if needed. So one of the things we're going to cover in this presentation around optimizing the set points is around glide. So we'll cover that in some of the later slides, but that's really important in making sure that you're setting your, you're making sure that you're getting the coil temperature that you expect to get. If you're used to doing 407A conversions and you haven't done a 449A conversion, these are the same exact 8 steps you would see for that. I wanted to highlight real quick, this is another good one to maybe take a screenshot of. So these are some of the different elastomers and gaskets that you could find in a refrigeration system. So things like Schrader fittings, Schrader caps, could be gaskets on receivers, on condensers, oil separators. So, you know, I just wanted to make sure that we put out some examples. It always comes up around, hey, okay, so you say change the critical elastomeric gaskets. Well, what gasket specifically are you talking about? So if you look at it from a performance standpoint, we talked about this before. What does performance mean? So capacity, COP, mass flow, suction pressure, discharge temperature. And across the board, 449A is pretty similar to R22 capacity-wise. We'll talk about capacity a little bit later. There's different ways that capacity is talked about, and on this slide specifically, I'm talking about the volumetric capacity. So this is essentially telling you, or the relative capacity is telling you, do I have enough compressor to meet the cooling demand? And for 449A, you would be expected to have enough compressor to meet that cooling demand based on the 22 design. Mass flow rate, so 449A has about an 11 to 14% greater mass flow rate than 22. So what that means for like expansion valve or line sizing is really not that much. So line sizing isn't really changing. Expansion valves, if you do not adjust an expansion valve post retrofit, I would expect it to have a couple degrees higher superheat in the evaporator, and that's because of both the relative mass flow rate in addition to the slightly higher suction pressure. R22, probably one of the best performing refrigerants that the refrigeration industry has ever worked with, but it does have one rather large flaw in that it has a hot discharge temperature. So any refrigerant that you retrofit to besides 22 likely will have a lower discharge temperature than R22, which is great. So from a recommendation perspective for 22 retrofits, if you have anything that you need to, if there's any kind of demand cooling on the 22 compressor, you just keep that demand cooling running, and you may not need it as much with a refrigerant like 449A. So for 404A, and this is where we're going to spend a bulk of the presentation, is because the steps are a little different. And if you don't know what you're going into with the 404A conversion up front, there certainly can be some surprises there that you're not going to want to see when you do these retrofits. So really, step one for this is reviewing the retrofit guidelines again. And in those guidelines, there's a key part about evaluating the low temp system demand cooling needs. So I'll show a chart on one of the later slides that kind of gives a recommendation for when demand cooling is needed for these gases, and it's close, to be completely honest. However, 9 times out of 10, if somebody comes to me and says, I have a low temperature 404A piece of equipment that has no demand cooling on it, and I live in an area that is hot in the summer, so I'm designing around like 100-degree condensing, you're going to see demand cooling be a recommendation for really any retrofit away from 404A. The other steps are pretty similar to the 22 conversion we just covered. So obtaining the baseline data while running on 404A. Again, like 22, retrofits aren't going to fix existing problems in the system. And then really just doing a check on the lubricant. So one of the nice things about these retrofits is because 404A is an HFC, it should already be running on POE oil. And the POE oil that runs on 404A will be compatible for use with 449A. The other thing you'll notice in step 4 of the 22 retrofits, it said change filter dryers and the critical elastomeric seals. For a 404A retrofit, it only says change filter dryers. The critical elastomeric seal issue that we just covered was really only focused on chlorinated gas retrofits. If you're retrofitting from an HFC to an HFO, so 404A or even 134A, you shouldn't have to change those gaskets as part of the retrofit recommendation. Following the TXV adjustment guidance, we'll cover this in a lot more detail in the next few slides, but following the TXV adjustment guidance, if I had to give you one thing to look for in a 404A conversion, it would be that. 404A TXVs, if you do not adjust the TXVs post-retrofit with 449A, 448A, pretty much any refrigerant beyond 404A, I can almost guarantee that you will start to see icy compressors. Adjusting these TXVs is critical to making sure that the system will be running as optimal as possible post-retrofit. And then the last 2 steps are also the same. So charging the system up, starting up monitor. Again, charge should be pretty similar. And then leak check, label, and optimize the set points if needed. So we'll talk about pain points for retrofits on one of the later slides, but really if you're looking or comparing 22 to 404A retrofits, 22 retrofits, you had to worry really about changing the oil, changing the seals. With 404A retrofits, you don't have to worry about the oil, you don't have to worry about the seals. However, low temp system demand cooling needs is something that you need to focus on, and then following the TXV adjustment guidance, which we'll cover on some of the next slides. So first, demand cooling. This is another great slide to take a screenshot of. This is from one of the Emerson application bulletins, and I use it generally as a cheat sheet for when demand cooling would be recommended by the compressor OEMs. So 65-degree return gas, I'd say that's probably a little bit on the warmer side, but you do want to design for worst case. So if you take a -20 evaporator and a, say, like 95 condensing, you're pretty much right on that line as if demand cooling is needed. So it says below the head fan, shift the liquid injection line up 5 degrees. So there's ways that you could get around it. But again, I think the compressor OEMs, they're going to know their equipment best, and they will give you the proper recommendations that are needed for these demand cooling recommendations. From my experience in the field and working with end users on 404A retrofits, I'd say most are putting it on. So TXV adjustments. To get into this, I wanted to give a little background on really how a TXV operates. And really during refrigeration operation, a TXV is balancing 3 pressure forces. So there's an opening force of the power head, a closing force of the suction pressure, and a closing force of the spring pressure. And at any time, those 3 forces are trying to balance each other to regulate the flow of refrigerant that is going to the evaporator. So I'll tell you up front, using 449A with a 404A TXV requires decreasing the suction pressure to achieve the same average evaporator temperature. So based on that, what would that do to the force balance above? So I'll give you like 5 seconds to really think about that, and then we'll cover it. So for those that figured out that with a lower suction, if you're decreasing the suction pressure, what you're doing is you're decreasing a closing force, which is actually a double negative, so the valve is becoming more open. So as we talked about before, if you don't make any adjustments to a TXV, one of the reasons for that is because you're using a lower suction pressure with 449A, that valve is tricking itself into thinking it needs to be more open than it actually does with the new refrigerant, which is leading to lower evaporator superheats. So how do you fix that? Well, you need to realign the force balance on this. So what you can do is increase the closing force of the spring pressure, or you could decrease the opening force of the power head. And really what you're going to need to do for these retrofits is probably both. So for 404A retrofits to 449A, 448A, or really any of the other alternative gases, you're going to need to close the TXVs. The TXVs are likely going to be they're going to need to be closed probably about at least a turn, if not more. In addition to that, it's been our recommendation, and this is something that we've really worked with the OEMs in the industry and contractors and end users and everybody to try to figure out what the best recommendation would be. And we believe it is to change the power element on a 404A TXV from a 404A element to a R22 or 449A charge. That really will help get you better control on the TXV. But one of the things to keep in mind if you work in supermarkets is there are going to be a lot of TXVs in those stores. So proper planning is really key if you need a bunch of power elements to make sure that you're planning for these 404A retrofits. So here's really the guidance on adjustable 404A TXVs. If you're looking at the suction pressure difference for the same average evaporator temperature, for low temperature systems, you're looking at about 4 psi lower to reach the same with 449A to reach the same temperature. For medium temperature applications, you're probably about 7.5 psi lower. Really what's on this slide is what we've seen work in the field just from being at supermarkets with contractors and working with them to see really how to get the best control. So when the suction pressure delta between two gases is between 5 to 6 psi, there really is likely enough adjustable range in the spring to try to reach target superheats. But again, that's not, it's based on experience and not really a hard line as to what is acceptable. There's other things that go into it too, such as the net refrigeration effect. So 449A has about a 20% lower mass flow than 404A at the same tonnage. So pretty much what that means is you need 80% of the 449A to boil off the same BTUs as 404A. So there's things like that that go into it as well. But if you need to give a final recommendation to a customer and make sure you're doing right by that customer, I would recommend changing the power element from a 404A element to a 22 or 449A type head to get the best control on those valves. This is another good one to screenshot. So, and the link or the form number below will tell you where to find this document. So this is from Sporlan, and it's a very handy cheat sheet that goes over everything from 404A or 22 retrofits, from 407A, 407F, 448A, 449A, and it covers a lot of the typical components that you could find in a refrigeration system, such as the elements, the EPRs, the filter dryers, the oil, the seals, and it'll tell you really what the recommendations are in a single chart for those gas conversions. The last thing I wanted to cover, because this is something that comes up a lot, is glide. So glide is definitely something that the industry, I would think you've probably seen glide by now, but in the refrigeration world, especially if you've been used to using 22 and 404A, glide might be a newer concept. And glide is something that, while it has been around, there are ways you can optimize it, and there's ways you can work around it, but having an understanding of what physically is happening with refrigerant glide is helpful in making sure that you're optimizing the system as best as you can. So what you're seeing on this chart is data from our systems lab in Newark, Delaware. So in that lab, we have freezers that will throw in controlled environments and hook up a bunch of thermocouples to the freezers to benchmark refrigerant performance. So what you're seeing on this chart is actually the temperature profile of a freezer that was running on 22 and then 449A in the condenser. So you can see on this chart, the orange line is 22. So as the 22 desuperheats, it hits about 90 degrees and then it's relatively constant. Whereas 449A, the turn, so that's when it starts to condense in a condenser, actually happens at a much warmer temperature because the dew point is greater than the bubble point for a refrigerant with temperature glide. And then as that refrigerant condenses, it actually cools off because of the glide. So all glide is it's a temperature difference across a heat exchanger. Glide has nothing to do with when you're a single phase. So if you're fully a liquid, fully a vapor, glide really doesn't do all that much. It's not really that important. But where it does impact some of the ratings that you might have seen for condensing units, for example, is in the heat exchangers. So again, this is one of the rules of thumbs we've had, and it's really how to optimize for glide. So one of the questions we get a lot is Dewpoint versus Midpoint. And it's pretty funny where the refrigerant manufacturers, I think, were the ones that were really stressing midpoint and the term midpoint. But honestly, I think midpoint is a little confusing, and I don't necessarily like the term. So I'll try to explain here how I think of it, and hopefully it can resonate with you guys. So you're setting pressures by dew point, right? When you look at a PT chart and you're trying to figure out what temperature you need to set an evaporator at, you'll take a PT chart and say, okay, if I'm at this pressure, it corresponds to this dew point. So all glide really is, again, it's a temperature difference across the evaporator. So in an evaporator, for example, you're going to come in cold, and then as you boil, because of the glide, you're actually going to increase in temperature. So I put two examples here, which could be good to screenshot, where, like, let's say you wanted to run a 20F evaporator with 7 degrees of glide. Essentially what you're saying there is you're going to enter the evaporator at 13F, and the refrigerant's going to boil and become saturated at 20 F per the pressure you set. You could do another example where if you have minus 20 F and you have that same 7 degrees of glide, you're going to enter the evaporator at negative 27 F, and then as the refrigerant boils, it's going to become saturated at negative 20 F. So if you don't adjust the glide in an evaporator, for example, you can see that your average temperature, so your average coil temperature, is actually a little colder than you would think you're setting it at. So what that does to a system, for example, if you're looking at cycle models, is it impacts capacity, it impacts efficiency, it could lead to frost generation in medium temperature applications. It's definitely something you want to look at. So I'm going to give you the way I wrap my head around glide and trying to set it, dew point, midpoint, is if you look at an evaporator, for example, for 449A, any of the products that I briefly mentioned beyond 449A, so 448A, any of the 407s if you're used to working with them, really I think a general rule of thumb is to simply add about 3F to your dew point when specifying or setting an evaporator pressure for any of those gases. So if you look at the examples here, right, if you were to set a pressure at 23F versus 20F, your average temperature goes from 16.5 to 19.5 when you're trying to hit a 20.5. So I think that's the easiest way to try to think about it, where, all right, you could even set it how you want up front, but no, you're likely going to be able to increase the pressure very slightly to optimize for the glide. One of the other big questions we get around glide is, so dew point, midpoint are condensing unit ratings, and around, okay, if I have a condensing unit that that was 404A and I run the calculation with 449A, I'm getting that I am needing upsized condensers, but all the refrigerant guys are telling me the capacity is equal. So what's going on there? So this is for 404A, and 404A has about 1 degree of temperature glide. So if you look on the right side of each one of the pictures, the first two values, the compressor capacity and net refrigeration effect for a refrigerant with low temperature glide, are very similar. So you're looking at 14,700 BTUs per hour for the dew point and 14,800 BTU per hour for the midpoint. However, when you start getting into the refrigerants with glide, that really no longer applies. So this is the same compressor, the same conditions, everything is exactly the same. And if you look at 449A based on a dew point rating, you're at 13,600. So going back to 404A, you're almost 1,000 BTU per hour different between 404A and 449A. However, when you look at the midpoint, you actually get additional capacity back because you're taking advantage of that glide and those temperature differences and running slightly higher suction pressures. So if you were rating a condensing unit based on dew point, I would think your condenser would likely be slightly oversized for the application. This is another good one to screenshot. So this is the cheat sheet. 1 pager, covers everything that we just went over. Due to time, I'm not going to go into it in that much detail right now again. But again, pain points for 22, oil, critical elastomeric seals, pain points for 404A, expansion valves, and the discharge temperature. And both of them have that control that we just covered with the temperature glide that you also need to look at. Again, this is a good one to screenshot if you have any questions on it. We get a lot of questions around things like HP80, 408A, some of those 502 service blends, and if you had to ask my opinion on it, that equipment probably has reached the end of its useful life and likely is closer to replacement versus it should be retrofitted. However, at a high level, if you have any questions on this, we can certainly help look at systems. The big things are if you take the pain points of a 22 retrofit, so changing the oil, changing the elastomeric seals, the pain points of a 404A retrofit, of changing the power elements, looking at the low temperature demand cooling needs, in addition to making sure that the equipment is compatible with POE oil to begin with, you will have everything that you need to do for an HP80 or a 408A conversion. These have been done. They've been done successfully, and it's been a way to extend the life of that existing equipment, which is the main goal of any retrofit gas. However, it is important for your customers to know that this older equipment is old, and like a retrofit isn't going to fix a performance problem, a retrofit certainly isn't going to fix the age of a piece of equipment. So you want to make sure that that is known going into it. If you're changing out a compressor, for example, in a 408 or an HP80 system, that might be a great time to look at retrofitting something to 449A. Real quick, 513A. Again, this is something you might not have seen that much going in the past, but going forward, I think it is a very useful refrigerant for the toolbox because it has a 56% lower GWP than 134A, and also is about half the GWPs of 448A, 449A. So if you have a medium temperature application, or really 513A can get down to positive pressures up to about negative 20 F. So there's even some selected low temperature applications where 513A could be a very useful product to look at if GWP is a concern. It's very similar to 134A. So if you look at the metrics again, capacity, mass flow, COP, suction pressure, discharge temperature, it's pretty close. From a retrofit perspective, you're not changing the oil, you're not changing the gaskets, you don't need to worry about the power elements. Post retrofit, your superheat might be slightly higher, but it's well within the adjustable range of a valve to dial in that superheat. MP39, much like HP80, 408A retrofits, people have done MP39, MP66, 409A retrofits to 513A because they're trying to skip a step. However, again, retrofits aren't going to change the age of a system, and that needs to be mindful going into it to make sure that the compressors can be compatible with POE oil. Real quick, some of the common questions we get from the industry that weren't specifically covered. The big one is, will fractionation cause any issues with using 449A? Really, the system effects on fractionation on refrigerants like 448A, 449A are insignificant. The industry has used refrigerants with Glide for a long time, and I always like to say dilution is the solution. So if you have a running refrigeration system, it's really hard to get preferential release of certain components such that it would cause issues in performance. If you have a leak, I'd say the bigger issue is that you have a leak, and topping off with liquid refrigerant will be the best way to fix that without having to remove the entire charge. Covered the largest changes you need to make to a system. So 22, 404, oil and seals, 404A, TXV, and demand cooling, 402A, 408A, all of them. Energy efficiency. So you need to make sure that you're optimizing for Glide if you want the best energy efficiency and capacity. And again, rule of thumb, for a product like 449A, you're probably going to need to run 3 to 4 degrees F higher than you would expect. One of the questions we get a lot is this whole presentation I've been talking about 448A, 449A pretty interchangeably. We get a question of if they can be mixed. So although they are similar in performance, different refrigerants should not be mixed. And this has been the guidance that's been put out in EPA section 608. And it's really just not a good practice to get into, because essentially whenever two refrigerants are mixed, a new refrigerant was just invented, and you won't be able to know the suction pressures, the discharge pressures, like your PT charts will no longer be useful. will your current leak detection system be able to detect new refrigerants? So any leak detector that can detect an HFC refrigerant can be used with these refrigerants. They should all be compatible. And a lot of the newer leak detectors, they should have products like 449A in their library already. So with that, real quick, just wanted to give a couple shout outs to some of the tools we have. HFC regulations fact sheet. So on our website, if you want the latest and greatest in regulations, opteon.com. If you go there, you can find all the regulations that are relevant to you guys today. We're constantly updating these documents. We even have specific documents. I would think most of the people on the call today are in the Northeast, but we have specific documents for places like California that has its own set of regulations. And then also we have great online training. So we have a YouTube series called Check Up with Dr. Chuck. So Chuck is one of our senior colleagues, technical colleagues at Chemours, and he does a really great job of walking through what's going on in the industry and everything that an end user, contractor, distributor would need to know to really make sure they're giving the most informed decisions to their customers. Technical support. Here's another good one to screenshot. I mean, we do a lot in the industry. So if there's any type of document that you need, feel free to reach out. We can always generate something. Trainings, we're always willing to work with anybody on training and getting the information out there that they need. And then this phone number is also a good one to have if you have any questions. So even if you're on a roof somewhere and you have a question, you want to get in touch with us, 866-433-8324 or tech2tech@chemours.com, and we would be happy to help you out. So with that, I thank you for any. I thank you for your time today. I know that was a lot to cover in 50 minutes, but if there's any questions, we could certainly go over them. And again, thank you for your time.
Andrew, this is Mark Love. We do have a couple questions that are in the queue. I'll go over a few of them. We're going to have a hard stop at 12:58 and then close the webinar. So the first question is, how does 449A differ from 448A?
That's a good question. So if you look at the components of 449A, 449A is a 4-component blend. It's got 32, 125, 134A, and 1234YF in the blend. And then 448A is a 5-component blend. So it has the 4 components of 449A. And then in addition to that, it has 7% 1234ZE in it. Quite honestly, much like I've talked about the two interchangeably in the presentation, you're not going to see a large performance difference between the two gases. So there's really not all that much of a difference beyond 448A is dependent on a ZE supply in addition to the other components.
Okay, thank you. We had another question. It says, I thought R438A MO99 was best for R22 AC applications. Can 449A be a retrofit for R22 air conditioning applications? Or are you talking about just R22 refrigeration applications?
No, that's a good question. I'll try to answer this. That there's a lot in that to answer, but for 22 refrigeration applications, that was really the focus of where 449A should live. 449A actually is not SNAP listed in air conditioning applications. So right now, if you have a 22 air conditioning unit and you cannot change the oil in it, MO99 would still likely be our recommendation. If you can change the oil in a 22 air conditioning unit, so if it can run on POE oil, then something like 407C would make sense. But the focus of 449A and its applications would be low temp, medium temp refrigeration.
Okay. Then one final one before I turn it over to Dale. Can you top off an existing 404A system with 449?
Much like you shouldn't mix 448A and 449A, mixing refrigerants is not a recommended practice. So no, we would not recommend topping off a 404A piece of equipment with 449A. You would want to fully recover the 404A. I mean, 404A is the new refrigerant gold, if you will, anyway. Making sure you're reclaiming that 404A is really key to a good refrigerant management plan.
Okay, thank you. We have a couple others, but we will follow those up in the post-webinar mailer. With that, Dale, if you'd like to come on and just say a few words and close out the webinar, that'd be great.
Yeah, Mark, I appreciate that. Hey, Andrew, that was incredible. Both, and same to you, Mark. You know what, we do a lot of training webinars, and we've done some prior on refrigerant changeouts. There's no doubt this is the best we've had, so thank you for that. Also, some accolades to our Meyer Supply team that worked on putting this together with Mike Santa Maria, Brian Jesse, and Roddy Wall. So, you know, during this transition through the AIM Act and trying to navigate our way through it, you know, our objective at Meyer Supply, and for Chemours too, is to provide you and your customer with a long-term solution, and also, as you can see here, to train the industry on proper refrigerant changeouts so that we can make it much more consistent, you know what, less callbacks. So I just want you to know each one of our branches are set up. In addition to this, they'll set up to accept all of your used refrigerants, and you'll receive clean evacuated cylinders in return. We also have a broad selection of transitional refrigerants in stock, and most importantly, all the support that you need to make that transition for your customer and do it confidently. We have access to everybody you've heard from here at Chemours, and you know what? If the job is large enough, we can also make we'll make a job visit if that's what it takes. If you get into trouble, call us. That's what we're here for. So thank you everybody for participating, and enjoy your weekend. We're done. Thank you.
Thanks, everyone. I'm going to be closing the webinar.
Thanks all.